by all the instrumentation. And first of all, it is important to know the temperature of the sample. So, monitoring the behavior of the electrical resistance of the nickel film, you can clearly see the cross through the Curie temperature, where we have the loss of the ferromagnetic properties of the nickel. So knowing the power to reach this point is quite easy to have a conversion between power and temperature. The Curie temperature of the nickel is 360. And in the chamber, in the making this kind of curve, I put the vacuum in the chamber just to avoid to lose too much power to heat the sample. With these curves, I just try to make a confirmation of the activation energy of the release of hydrogen from that film. And I used several cycles stressing the cell at different temperatures for the same time, having so isochronal curves just to calculate the activation energy. If you look at the same cycles on the reference nickel that I forgot to indicate in the first slide, the first cross section, that together with the sample under stress, I have just a reference nickel layer just on the top of silicon dioxide without hydrogen inside. So I can perform together activation measurements of the hydrogen film and also taking under control a reference nickel layer, not absorbing the hydrogen because on top of the silicon dioxide. You can see here 2 cycles on the reference sample, no significant change in the curve of the electrical resistance. So, this is an example of the curve for the activation energy calculation that confirms quite well what is reported in literature for the release of hydrogen from silicon hydride. So stressing the cell just to understand what happens when we try to load from the solid source the cell. We can see 3 phases. The first phase is just the heating phase of the sample. We have the log of the time, so in a few seconds, less than 1 minute, we have the cell at the working temperature. If we stay at that temperature for a longer time, we can follow the increase of the electrical resistance, and at a certain point, maybe when the loading is enough, you can see a third phase with a rapid increase of electrical resistance and the broken the break of the cell itself. After these cycles, looking at the cell, we can show many points, many hot spots where the nickel is melted. If you enlarge this picture, you can see many small drops of nickel layer. We have here electronic microscope photo showing the destroyed part of the resistor. Just to confirm that it was the hydrogen loading from the solid source, I made some experiment using hydrogen in the chamber. In this case, I was forced to use higher power because the pressure of hydrogen outside the cell decreases a lot the thermal resistance of the cell. But, okay, with this configuration, I could stress, in this case, both the reference resistor and the sample and the cell. And after many experiments, I destroyed all the cells that I stressed. And also in this case, I could see many hot spots due to melting of rising of temperature and melting of this nickel cell. I did some chemical reaction calculation. I didn't find any reaction able to get so high temperature. So I suspect that these experiments are very similar to the experiments that other researchers in the field of cold fusion made using nickel layers and hydrogen. Okay, I think that I can stop here. I have no conclusion in my work because the work is not finished because I destroyed all my cells and I'm preparing more suitable to have heat production measurements. So next time I will show you new results. Thank you.
Thank you very much. We have time for questions.
Yes. Have you done any chemical analysis that you film afterwards?
Yes, I tried to make with a micro X-ray analysis, but I found many elements that I used for the fabrication of the cell, but no difference in the zone with melted nickel and the zone with not melted nickel. No differences. But I found different. But aluminum, I used aluminum, silicon, and so on. So, and the material used is very, very low. So,
Larry Forsley, JWK. On that second set that you did with the hydrogen gas loaded from sitting on the silicon dioxide substrate.
yeah.
Am I correct that you ran no current?
No current.
No current. That was
No
just
current.
absorption of hydrogen and it melted the nickel.
This is the nickel layer just on top of silicon dioxide. So no hydrogen inside. No hydrogen below this layer, this nickel layer. And no current was flowing in that layer.
My name is Srinivasan from ICCF. We have reported in ICCF-7 at Monte Carlo our results with nickel, self-heated nickel wires exposed to hydrogen gas, and we have reported there. We also found hotspots in some of our geography, and the interesting observation that tritium production in the nickel wires were non-uniform. Some sections of the nickel show a lot of tritium, and others did not. And that is proceedings of ICCF-7.
Yes, I know the abstract of your presentation, because till 1995 I was just an observer of the field. And I did some experiment using a biasing of the nickel resistor. I has the impression that the reaction is faster. It's faster. But the location of the melting spots are not well identified. It's quite random.
Second speaker asked about possible blank. What do you think it can be done? If you give similar power, because resistance of the meter increased after loading, can you compare data in compare the same way, or we have some more idea about it?
To do a blank experiment.
Yes.
To do a blank experiment may be done just together with a black experiment. As we
So you
do.
see it's completely equivalent to make the same chip.
Yes.
No change without temperature interchange solely. So completely safe.
If I follow the resistance change in the reference resistor in the let's say we call black resistor, we cross the Curie temperature with the same power. So the power of the chip is quite uniform. If I press without hydrogen outside, just using the solid source, I can look changes only on the black resistor. The black resistor remains virgin. That's
No
it.
damage. So it means you have conclusion, because you can compare. Now you have conclusion actually,
Yeah.
because you destroy what the stock from nitrogen.
Yes.
So you have conclusions.
I'm not so sure.
Okay, thank you very much for your interesting
Okay, thank you very much.
Next, we have Professor Matsumoto, mechanism of electronuclear collapse.
I'm Mastromatteo from Hokkaido University. Thank you very much for giving me more 50 minutes. Let me go back a little bit earlier experiment. I have been carrying out an experiment USA, not mine, under four-class experiment. Experiment is very simple. Here, 50 millimeter beaker, thin wire, metal wire, 0.5 to 1 millimeter diameter. The thinner material is used, and the reference platinum and DC charge. And in 1994, in April, I first observed a very curious spot on the surface of the electrode. And this is the ivory curve. The voltage is increasing. In the low voltage region, we have gas evolution and the linear relationship between ivory. But about the 40 volt, the sound suddenly stopped very quietly, make quietly, and simultaneously microspark appeared. And the current is strongly suppressed. And then microspark appears with a structure like this. This is the cathode, and here we have a pinch region. And gas is almost completely suppressed, not evolution. So microspark appears from the bottom, and increasingly the voltage more. These are the number of the microspark increase, and eventually completely cover the cathode. And I don't know what's the condition in here, pinch region. Probably critical hydrogen fruit is formed here. And in this area, the compression is made by the electric potential. So here we have a curious microspark, and this is found to be a ethonic hydrogen cluster, as I said yesterday presentation. And this is a DC experiment, and I try to make the pulse AC discharge experiment to completely destroy the cathode to have a nuclear collapse. And this is the Passell AC USA experiment. And here, electrode, red wire was used, and solution is potassium hydroxide and cesium carbonate. And the reference electrode is carbon. And the carbon is, at the same time, carbon is a monitoring of the particles. And polished like a mirror, and trained in the alcoholic solution with ultrasonic vibration. And when they flash here, flash is like this, 20 milliseconds to 800 millisecond flashes, couple of shots employed, and products scattered, caught on the surface of the copper plate. And those products are examined by scanning electron microscope. This is a lead and cesium solution. This is a lead ball. And here you can see the very curious structure. This is the network of the material, lead, I call the atomic state. And this network is broken. We can get this needle, right needle. So we have very interesting needles. This is the red wall. And the red wall is covered by this cesium. Cesium is also ionized. And cesium cover compressed the lead. This is the lead. Over the surface, lead, cesium, carbon, and oxide. This carbon is electrolyte carbon. This is interesting. The broken lead. Here we have a curious structure, and a tiny grain of lead is produced. And I don't know why this structure is formed. Probably eddy current has a very important role. This is the atomic lead, and there you can see the similar network. And this is a little bit of broken lead ball. And when the explosion takes place, these lead debris are scattered like this. And when the explosion stone completely destroyed, and when these debris is expanded, you can see very interesting structure like this. This is lead. Lead has a very curious structure. This caused by the atomic electrode. And very important product is thin film. This is a thin film, consists of mainly carbon and some amount of oxygen. And this is the carbon film. Carbon film generated, and this is the very clear evidence for the generation of the carbon film, COK, and that is the here. This red ball compressed by the atomic bonding, and in the red ball, the carbon film generated. And you can enjoy the very lots of varieties of the generation of carbon. And this is the red ball. Here, exploded the carbon is also contained. This is the carbon. Yeah, you can see the book of Electrode at the desk. When the compression is strong, lots of the amount of the carbon film produced, and the dead body becomes very small. And the carbon, oxygen, RB, silicon, these elements are included. Okay. There are several lots of variations here. And this is interesting. This is Nero. So compressed by these atomic depth, and directly these carbon is appear from the ball. This is interesting. From here, carbon, including carbon and iron is included here. This is the EVX spectrum. Iron is here. The carbon, this is the oxygen. Carbon is this is carbon is here. Okay, this is a whole red ball. From here, carbon brings solid. And this is a dead ball, dead potassium. Copper is the base metal, and the oxygen is here. But on the carbon film here, carbon is here. You can see the EDX spectrum. Carbon clearly appears. The oxygen is also appears. And the other is very hollow, and hollow red ball. Inside, the thin film is coated, and this hollow ball is gives this structure like this. And this hollow red ball is produced from the atomic depth, compressed here, and these hollow ball is produced just like popcorn. This is a similar pattern. And the other is this tube is also produced, and here, and this is the thin tube. Like this. Here, carbon. This is carbon, oxygen. That in the exit, these elements is included. Here, these elements, many elements up to the iron is included. So this is the other interesting picture. This is a cluster. Carbon cluster is assemblies. And here, one carbon lead ball is transformed these tube. Here, it's very interesting. Here, these are elements are included here. Carbon to iron, these are silicon, aluminum, these elements are produced. And this is a very like fermenting protein, as present with the Mastromatteo, not only the Japanese fermented soybean. And this is a hypothetical theory. We have to explain two different kinds of materials. The first is tube, carbon tube. The second is carbon wheel. They are simultaneously produced in the ball. So here, nuclear collapse takes place, and tiny black hole produced here. They are connected to the wormhole to lead to the white hole. And here, nuclei completely destroyed. But during passing through the wormhole, the conventional material like this degenerated. And however, too much materials compressed here. They cannot pass through this way, diameter is very thin, so that they explode it back. Then we have a film. The heavy elements are distributed uniformly here. Then these are heavy elements produced near center. The lighter elements on the periphery. This is my hypothesis. Thank you.
Thank you very much. Welcome to questions.
I was wondering if this could be, the little balls could be formed like hail is formed on the Helmholtz bilayer of the electrode. They're going to be rolling around, inflating, and then you're going to get weird little structures like that, like I guess a bulldozer made that one or something.
This is my hypothesis. And some centrifugal effect is works here. And when the material is generated, they are rotating. So heavy light elements produced in the periphery, and the heavy elements in the center. This is my hypothesis.
Thank you.
Okay, thank you very much, Professor Matsumoto. Next, Dr. Miles will discuss radiation measurements at China Lake, real or artifacts.
This report's on work we did several years ago. Our focus at China Lake was not radiation, but safety officer insisted that we do radiation measurements, make sure there's no danger. In fact, we were even threatened to be shut down at one point because his restrictions on what we could do, since he thought it was a dangerous type of experiment. This work was done by myself and also Dr. Bush, who was on a postdoc fellowship at that time working in China Lake, now at the University of Texas. As I mentioned, it was imposed due to safety concerns. We put detectors at the top of the cells above the water bath, and some later studies indicated that at that location, we would not be able to detect anything with energies lower than about 50 kV. Anything with lower energies would not escape from our cell in the water bath. This is some work based on our system done at the Naval Research Laboratory. So these are at the top of the cell above the water bath. We had other detectors too, but due to safety concern, we had also badges set up at different distance away from the cell, radiation badges. Our experimental equipment, we had a Ludlam model 2200 scalar rate meter. Actually had 3 because we had 2 different sets of experiments and several different detectors. A Ludlam model 15 neutron counter. This just gave off a beep. This was never connected to any counter, and it just beeped when their neutrons very, very advanced actually. We used Ludlam GM Geiger Muller counters and sodium iodide detectors, and also from a different company called TGM detectors. So we used Geiger Muller detectors from Ludlam and also from another different company. And we got anomalous counts with both types of detector steers. Then I mentioned we had the radiation dosimeters, also different positions away from our experiments, assisted on by the safety officer. We never claimed to be experts on radiation, but we had experts from the Naval Research Laboratory come and check our techniques, and essentially they agreed we were doing things correctly. In fact, while they're there, we measured the plateau again. We've done that previously with an iron 56 source and a cesium 137 source. In the background, this is counts per minute, and this is the voltage applied to the tube. And you should set your operating voltage right near the beginning of this plateau. You don't want to set it over here where small changes in voltage can make large differences in your counts. So they agreed that what we were doing was basically correct. And most of the time, we did not see anything strange. We usually counted over a 12-hour period, and this was printed out. So we're counting over a long time period, and these are thousands, counting 32,000, for example. And this is over a period of time, different days. This is plus or minus 3 sigma boundary, and you see that under normal conditions, there is nothing outside plus or minus 3 sigma. Here we had ordinary palladium D2O electrolysis going on, and everything was normal. We had no experiments going on during this period, no difference. We had another experiment set up over here, actually 2. We always ran 2 cells in series, and again, nothing unusual. That was the normal behavior that we saw with these detectors. However, we later went to a co-deposition process. This is reported by Sam Spock at Navy Laboratory in San Diego. This is different than normal palladium electrolysis. You actually start with palladium chloride, the complex in solution, and you plate it out on a copper cathode. That's one of the cathodic reactions. Is that you actually don't have any palladium except in solution at the beginning, and you plate it out onto copper. At the same time you're plating it out, you're electrolyzing D2O and depositing deuterium into the palladium, or maybe coming off as a gas. That's why I call it co-deposition. Depositing palladium and deuterium at the same time. And this gives you a nice clean palladium. You don't have to worry about impurities. It is a nice technique. It should be studied further by other people if they have funding. At the anode, we have the oxidation of D2O to give oxygen. But the problem, this is in a lithium chloride solution. We have palladium chloride, lithium chloride. So one problem here, you have chloride ion in solution, and you do get chlorine evolution as well. And so that's a thing that I think I'll show later caused some of our problems is the chlorine evolution that also took place. You could sometimes smell the odor, and there were other signs, bleaching effects. You could prove that it was chlorine. This shows an example of a co-deposition experiment. We had our normal counts going on through here. The open circles are when the cell was still off. We hadn't turned anything on yet. And then the black circles is when we turned on the current. And you see, when we turn on the current right here, our next count, the rates is much higher at a 73 sigma level based on the 12-hour period that we counted. We only had 6 milliamps running through the cell because we're depositing palladium. We wanted to do that rather slowly. So it's a low current. Under these conditions, you'd plate out all the palladium in about 24 hours that was in the solution. And these high counts continued for several days in this case, and we increased the current here to 500 milliamps, and it continued also. But eventually, under steady state conditions, if you don't change anything, it eventually dies away. As you see, it just died away, even though it's still running. The counts went back to normal, and then we turned the cell off, and it stays normal here. So the effect doesn't last forever, but it does last for several days in general. A couple other things on there, I don't know they're important, but we did add thiourea right here, and the counts did pick up after we did that, but we don't know, we don't have proof that that really made a difference, but Stan Kwok always said that seemed to help his effect. He was trying to measure tritium, and that seemed to increase his tritium production in his experiments. Well, this happened quite a few times, and we thought maybe it had something that could really be promising and could be studied further. And the Naval Research Laboratory in Washington, D.C. had better equipment for radiation measurements. They had an X-ray detector, germanium detector. So one of their experts came to our laboratory, and we tried to reproduce this, but we turned it on here, nothing would happen. So we set up another experiment. They were only there for a few days, and we had to do this rapidly. Set up another experiment, and still nothing happened. In fact, because of these rather large detectors, they were screening our usual detector somewhat. So you see our counts, if anything, are below normal, not above normal, because of blocking and screening by these bigger detectors. And this is very frustrating. We have these good detectors here, but we could not see the effect even with our detector, let alone their detector, while they were in our laboratory. And because of the short time, we ran these very quickly, maybe 1 or 2 experiments a day. And as I'll show later, that's perhaps the problem that we had, trying to do things too quickly and not allowing time to let the chlorine clear out of our system. We had the gases went through some tubing into an oil buffer, and so chlorine probably was still present in those gas tubings. And apparently, if you didn't flush those tubings out or give a couple of days time for the chlorine to dissipate, somehow this really drastically affected our results. At least that's what it seems to be. That is the conclusion that I finally came up with at quite a later date. In fact, as I mentioned, the chlorine evolution, you have the regular detail oxidation, but also the chloride oxidation. And whenever we had possibility of chlorine from a previous experiment, we never saw this effect in 11 different experiments. We had 0 out of 11. Whenever we had flushed out our system with nitrogen, we just happened to do that. We weren't aware of the chlorine problem. But going back to check the data, when we had flushed out the system with nitrogen, we had this anomalous radiation 5 out of 8 experiments. And if we weren't rushing our experiments like we were when NRL was present, the people from the Naval Research Laboratory, and took our time to set things up and allowed a little more time between experiments, 3 days. After 3 days, the chlorine would probably dissipate anyway. Then we had this effect 3 out of 5 experiments. So 5 minutes, okay. This happened quite a few times. This was another experiment. Everything was off, everything was normal. We turned it on here. It took a little bit longer to develop, but again, it goes up here to 25 sigma, and then here at 8 sigma. But when we had it off, we always had a normal count when the experiments were off. We have also seen this effect with solid palladium rods. Normal palladium electrolysis is not co-deposition. But we know when we use palladium rods, it takes longer to load them up. In fact, it usually takes 1 or 2 weeks before we see excess heat. They probably load faster than that, but it still takes 1 or 2 weeks before excess heat shows up. This shows a palladium silver alloy cathode, 2 cells run in series again. And we had two different detectors. One Geiger meter detector as before, but here we had a sodium iodide detector which gives you more counts. This is counts for sodium iodide over here at 450,000 for 12 hours, as you see here. In this experiment, it took time. We had the cell running here, but it took about 14 days or maybe 15 days here before we saw any anomalous radiation effects. And this is very similar to what we see with excess heat. It takes about 1 or 2 weeks before excess heat shows up. And we again had rather large counts up into this region. This is a Geiger meter count clear up here, another one clear up here from this particular detector. The sodium iodide detector, after about 7 days, started to show somewhat higher counts through this region. So here we had two different detectors showing high counts nearly at the same time. They were, however, positioned at two different cells. The cells are about like this distance apart, one detector with one cell and one detector with the other cell. So they were not exactly making the same cell at the same time, but they were close together. In some studies that Ben Bush did, he just brought through this for me a few minutes ago, but, and I also did this. When you would put the detector near the cell, the counts would go up. If you moved it far away, it would go down. Near, it would go up, and you could do this. When it was near the cell, the counts were higher. When you moved the detector away, the counts were lower. And so the counts, whatever we were seeing, did trace back to the cell by the roughly the R-squared distance as you would expect. I just want to mention the later Stan Spock, because of our work partially, he set up experiments to really look at this radiation more in detail in San Diego. He borrowed an X-ray detector to position right close to his cathode. To really look at this accurately, you need to get the detector as close as possible to the cathode. He wasn't trying to do excess heat like we were, was not in a water bath like we had, but he positioned it right as close as possible to the cathode, did co-deposition. I just, again, this is a drawing I just did an hour or so ago. And he has published a paper, it might be interesting to some of you. I didn't write down the whole title, but Emanating Radiation. He did see evidence for X-ray production from his cell, and some lines in this vector. I think one line near 21 keV, which would be the K-alpha line of palladium. It's not a real strong signal, but there is a signal there. Plus, it also at higher energies, there's evidence for X-rays. This is in Physics Letters Day, Volume 110, pages 382 to 390, published in 1996, if you want further details on his work. And then just to summarize, the anomalous radiation, real or artifact, of course we think it was real, but because we often could not see it at the same time with two different detectors, we never published this. This is in our final report written for the Navy, but we never tried to publish this in any journal. The reason I would say you could argue it's an artifact, it was never reproducible like many things in cold fusion, and many GM detectors we tried were blind to this effect. However, I might add that no two GM detectors were ever the same. When we checked their plateaus and other characteristics, every detector was unique. There are no two detectors that behave the same way of any that we ever tested. The arguments why it's real, well, we've seen radiation by X-ray film exposure quite early on by several different GM detectors from two different companies that we use, and also by a sodium iodide detector. And I think one of the strongest evidence, this effect required only a few hours for co-deposition experiments where there's rapid loading. But it always required 1 or 2 weeks before it would show up if we use solid cathode and ordinary electrolysis like you do for excess heat studies. And we saw it decrease when detectors were moved away and increase when we brought it back to the cell. And we never saw anything strange, no anomalous counts when experiments were not running. Okay, thank you.
Questions?
Hello, I just have a quick comment. I mentioned that with regard to the possibility of a neutrino source or something like that, or an interaction with that, there's a 21.3-day cycle of solar neutrinos, and I just noticed that it was like a cells and I start making the issue of external sources and patterns in their sort of time cycle might be effective on these results.
Well, in many cases, when we're doing ordinary electrolysis, we would go sometimes several months and never see anything unusual. Of course, it would have been better if we had another detector always running to measure the background and thinking was unusual happening, cosmic radiation and so on. That would have been even better if we'd done that. But I think you go back if anybody wanted to affect the time period to see whether there was solar neutrino buses during that time. I think that's what's possible if we wanted to do it.
When you did your co-deposition experiment, what kind of cathode did you use as a substrate?
We always use a copper substrate, but I think Stan Spock has used other things like nickel perhaps. But everything we did was always with a solid copper rod that we deposit the platinum onto this copper rod, about the same size as the plate electrode that we usually use.
At the back, sorry.
Yes, I'd like to make a comment. Standard electronic theory, one expects whenever there is electronic noise to be all around the circuit. Anything that can be detected locally from a cathode or an anode is just outside the standard artifacts that are known in electronics. Routinely, I pick up such signals in various diagrams, and I have established that they are not just the standard electronic noise. There's something that needs to be explored, and it's not just the usual radiation that have been, your cameras have been calibrated for, so that this is the reason we detect the different cameras detect different signals and pickups. So the main standard criterion is whether you pick up all around the circuit or not. If you pick up all around the circuit, then this is a standard noise, electronic noise. If that is localized in a node and a cathode, then something else that is related to something we don't know yet. Thank you.
That's a good question. We did think about that. I forgot to mention that, but we thought seriously about electronic noise. Also, the experts in the Naval Research Laboratory, they explored that also. And to test that, we could run everything on battery power. So we would switch everything to battery power, unplug all the instrumentation, and when we had high counts, they would persist. Nothing would change by going to battery power in our system.
Yeah, I mean, any electronic noise will be all around the circuit because anything that is somewhere in the circuit there is a disturbance, and that propagates along the leads and the conductors you're using your battery and everything else. If that is localized, at least it's not a standard electronic noise.
Right. But under normal conditions, we would run things exactly the same with the same currents, the same cells. In many cases, we saw nothing unusual.
John?
I understand that you were having pretty long counts, like every 8 hours, integrating over 6 hours or 8 hours. Is that what I understand from those charts?
Yeah. Normally we would integrate over 6 hours or 12 hours.
My real question is, did any of your passive or film things show anything at any time during all this? You mentioned, first I haven't read your time report, but did you report any of the film darkening or the passive detector experiments?
Oh, with X-ray films and everything?
Well, whatever you had in the way of passive films or integrating receptors.
In the early study that we saw high counts. In fact, that's when we did the heat helium study, actually. We self-produced heat. We also, the first heat helium studies we did, we had a dental X-ray film down in the cell near one of the cathodes. And both self-produced and excess heat, the film darkened. We tried that many times afterwards, but of course we often weren't getting excess heat. We never saw that darkening of the X-ray film again.
Is that in your report?
Yeah, that's in the report. Right. We had great difficulty reproducing the darkening of the X-ray film. We tried many times, but we could not get that effect again.
Thank you.
Yeah, during your co-deposition experiments, when you were seeing these effects, were you getting any excess heat?
The excess heat was difficult to measure in co-deposition method because often we would get some recombination always had to separate out. This is only case you ever saw serious recombination because the plating would break loose and the pull in solution, and then you could get some recombination. But basically, we never could really correlate very well the excess heat with the radiation. In some cases, we saw both. Other cases, quite a few of these cases with cold deposition especially, once we corrected for the cold deposition, the recombination effect, there was no excess heat there, but we still saw the radiation.
What about in the case of the palladium, when you did it with the palladium rods and you saw the radiation? Were you getting excess heat then?
In a few cases, but quite a few cases, like the one I showed in the top of it, was palladium silver alloy. That was made by NRL. We never saw excess heat with that particular sample, but yet we saw this radiation effect. So there wasn't a very good correlation between excess heat and radiation effects we saw.
Okay, next